Now we're going to talk about viscosity. Up to now we've considered static fluids, and now we're going to look at stuff that moves. For the mechanical engineers, this is part of life. For the civil engineers, this is frequently reason to panic. Because that's just the mentality. I'm teaching as somebody who has taught both mechanical engineering courses and civil engineering courses, and have also worked in industry where I sold and specified and manufactured a dynamic mechanical product into an industry whose mindset is more static. Now this is changing, but still it's a rough generalization. So with that in mind, let's proceed. Up to now we've talked about static fluids, and static fluids do not have neither shear, so therefore they're stressed in the same place. What happens when things move? Well, basically what I think the best way of illustrating this is to think about something that most of you at some time in your life have used, and that's air hockey. You put the puck on the table, you put the money in or whatever, and air flows out. And you've got this table here, and you've got this puck here. And the air allows us to have a film between the puck and the table. And then we hit it. We hit the puck with the puck, and if we don't have an opponent hitting it back at us, let's just say we just take it, put the table, hit it, and let it go around. Sooner or later, it will stop. Why? Well, the reason for that is simple. Because the fluid is moving, and because it has the property of viscosity, first of all, boundary layer theory tells us that ignoring the effects of the blowing air upward, the velocity here is zero because the table is stationary. The velocity is u, which is a CFD convention I will explain later. And for Newtonian fluids, I'm going to basically state that before I define it, the velocity varies from table to puck in a linear method, and in the process of doing though, puts a shear stress or shear pressure or whatever on the puck. Over time, that will resist the motion of the puck, which is the puck is basically when it's released, it's kind of like a pull, kind of like a pull, where you've got an energy of mv squared over 2, but while this is dragging it, ultimately it stops. You'll have the same thing with Coulomb friction, only usually Coulomb friction happens a lot quicker. But that's only because this is air. First, let's go to that. Viscosity is the property of a fluid, whereas it has shear stress, where we have shear stresses during motion of the fluid. The formal equation for this is the shear stresses are equal to the viscosity, which we'll define as mu, times du dy, where this is y and that's x. We're not too worried about x in this deal. We can, if all these conditions are perfect, we can estimate the shear stresses and ultimately how long the puck will go around the table before it stops. Assuming, of course, that it doesn't lose a lot of energy in the impacts on the rim. But that's a different story. That's not what we're talking about. If you look in your, by the way, before I go further, I kind of neglected it, I have a monograph on this subject called Variations in Viscosity. And it actually goes through this theory in detail, and it actually produces this formula right here. And this formula right here expresses this reality right here. So therefore, all fluids have viscosity. You will hear fluid mechanics and fluid dynamics people talk about fluids that have no viscosity, inviscid fluids. The only place where inviscid fluids can be found is in somebody's computer. All real fluids have some viscosity. Air has some viscosity. If that were not true, then the puck would go on indefinitely. It's low, the density is low, the viscosity is low, but it still has it. And of course we know that water has viscosity, but we also know that motor oil has viscosity. In fact, motor oil's viscosity is used to ensure a film, particularly when we go round on this thing, and going round on this thing is one of the things we're going to do, you get the same shear, and as long as the viscosity assists in keeping this lubricated. If the fluid's viscosity becomes too thin, it breaks down, you will have metal-to-metal contact or metal-to-plastic contact or whatever you have, and in the end will not be pretty. So that's why we have lubricants. So viscosity can be used in our favor, but it also comes with a price, and that price is that they will have energy consumption. Now, we continue with how does it vary? Is viscosity a constant? Can we just set it and forget it? Well, the answer is no, it's not. One thing that is obvious is that viscosity, I say obvious, I mean, if you've worked on any equipment and whatnot, you know that viscosity varies with temperature. That, as generally speaking, as a temperature of a fluid goes up, its viscosity goes down. So we probably need to rewrite this at a certain temperature, as if this drops, then the shear stresses drop. And once that happens, then we have lower viscosity and lower losses, but also we have lower lubrication. For the purposes of this experiment, we're not going to spend a lot of time worrying about the temperature effects. That's not the primary objective. Now, it's very possible to construct an experiment if you can vary the temperature to see the different temperature effects. That's not really what we're going to do this time. We're going to focus more on the effects due to change in mu because of shear rate. Now, let's do a definition. I kind of blew past it in the beginning. This kind of assumes that the viscosity for a given fluid is a constant. This kind of assumes that the viscosity is only a function of temperature. If we hold the temperature constant, the viscosity will be constant. That is true if the fluid is Newtonian. If the fluid is Newtonian, then we have a situation where it is independent of shear rate. Shear rate fast, shear rate slow, it doesn't matter. The viscosity is the same. If, on the other hand, this becomes a function of, well, I'll tell you. That's why I do handouts. Of these, both of these, this is Newtonian, and this is non-Newtonian. Okay, so non-Newtonian. The question is, and non-Newtonian fluids are common, but they are not necessarily easy to analyze. So therefore, how do we find out if a fluid is Newtonian or non-Newtonian? The way we do it is to analyze is to basically vary the shear rate. In this particular, if we have, for example, I'm going to take out the outside. If we have a cylinder, and we're going to see this, and we rotate this with some kind of omega, we'll have a surface, and we're going to talk about the surface velocity when we get to the rotating drum. We have a certain velocity. If the fluid is Newtonian, for example, then we get a shear rate. If the fluid is Newtonian, no matter what rotational speed we run this thing at, we should get the same viscosity. If it's not, we won't. And in that particular case, this is what, and there's a couple of ways of doing this. And I'm going to, the first way, and the way you see in many textbooks, is like this. You see charts that look like this. This is rate of shear and versus shear stress. A Newtonian fluid, these two will be a nice linear relationship, 0 rate of shear, 0 shear stress. Fluid static. As you increase the rate of shear, the shear stress will linearly. If you have a fluid that actually starts out going up very fast, it is called pseudoplastic. The best known pseudoplastic fluid is human blood. Human blood's viscosity does not, as the rate of shear increases, the increase of the shear stress diminishes. And that's useful because of the way it's pumped. The heart pumps it in cycles. In other words, it's not in fact, no pump is truly continuous. It's just some have very fast pressurization and release cycles, like you do in hydraulics with piston pumps or vane pumps. It's kind of slow, kind of like these old hand crank well pumps you used to see in the movies sometime. And on the other hand, if you have a fluid that starts out dilatant and then increases fast, a dilatant fluid starts out slow increase and then comes very rapid. And then you've got purely plastic fluids that really are in the twilight zone between fluids and solids, where they actually have a shear stress at no shear, which violates the definition of fluid that I gave you earlier, but fluids but are not really solids. Okay, with that in mind, what can we, and if I could monitor the rate of shear and the rate of the shear stress, I could get this. And if I see the trend line going up, then I will, then I can figure out what's going, then I can figure out whether it's pseudoplastic, Newtonian, dilatant, or whatever. But there's an easier way. Another chart you will see in some books looks like this. It starts out with viscosity versus rate of shear, which is actually, it's the derivative of this, or this is the integral of this, depending on. In this particular case, Newtonian fluids have flat. No matter what the rate of shear is, the viscosity is the same. If you have a pseudoplastic fluid, it'll do like this. Now, with pseudoplastic fluids, it doesn't have to curve like that. It can be a straight line down, it can be kind of a rough, but as long as the trend is downward, you've got a pseudoplastic fluid. And on the other hand, it goes up, down. Also, if you've got purely true plastic fluids like up here, they can have a flat, but they are not necessarily Newtonian, truly Newtonian. So those are the differences. So obviously, the way in which we can measure it, how do we do this? Well, the lab, basically what we're going to do. Now, in my narrative variations on viscosity, I talk about the old Thomas Stormer viscometers. Praise God, we've gotten rid of them. And we are going to have new viscometers, new Brookfield digital viscometers, where this process is going to be a lot simpler. However, the concept behind them is the same. I can measure a viscosity, and if I can measure a number of data points, number of shear rates or rotational speeds of the drum, I can determine the whether the fluid, if I give an idea of what the viscosity is, something that wasn't easy with the Thomas Stormers, and I can also determine how it varies, whether it's Newtonian, pseudoplastic, or dilatant. And that pretty much is the object behind this experiment. The concept is basically the same as it was before. It's just that we have a little bit more modern equipment. We can do this more directly than we could in the past. But there are some things which I'm going to caution you about. One of them is, let's go ahead and erase all this. Like I said, all of this is in my monograph. You can read it, take it in. There are two ways of measuring viscosity, expressing viscosity. One of them is to use mu, which is the dynamic viscosity, and the other is nu, which is kinematic. This is the kinematic viscosity. This is dynamic. And we will be obviously measuring this. Now, for an incompressible fluid where this does very little, if any, then this relationship is pretty simple. If you get like air, things get a little more complicated than that because you've got different variations in density. As a general rule, if that's not an issue, it's much easier to use this moving forward than this. Why? The units in this are either units of this are either in feet squared per second or meters squared per second. And these are fairly easy to use. These you always get messed up with G sub C, particularly in the US system of units. So I would strongly recommend that obviously this is what the machine will measure. I would suggest you use these values for future experiments. We'll see this when we get into the later experiments such as flow metering, and certainly we'll get into it with the wind tunnel. So with that in mind, also I have some in this document, some other examples of the use of this, and I also have some typical values for air and water. You will find these useful. Just store these in the back of your mind instead of fishing around on the internet. You will find these useful for future reference. So that's pretty much it in terms of what viscosity is. You can read the monograph and take a look at it. So let's go to the lab. Again, we'll see you in the lab. Now we're coming to actually measuring the viscosity. And what you're looking at is a Brookfield viscometer. This is a very common type of viscometer. You'll notice that the white area at the top has all the sensors, the motor that actually turns it, turns the spindle in the bottom, and it also has the readout for it. We're going to see all that in action in just a minute. At the bottom, hanging down from the bottom, we're actually screwed into the motor capstan is the spindle, and there's a guard around that spindle, which is used primarily. There are some measurement compensations for this, but the big advantage of using a guard is that you do not have to worry about it. It helps when you're setting the beaker up below it to keep from hitting the spindle, which is very fragile. So what we're going to do is we're going to set this thing up, and we're going to measure for the fluid we have in there, which is corn oil. Now, corn oil is an interesting fluid, and vegetable oils are actually found very often they're found in lubricants, and also there's also biodiesel and that kind of thing. And they're very useful in areas where you have environmentally sensitive regions and you don't want to use petroleum-based products. Then you can put your hydraulic system, set it up with vegetable oil of some kind. And you can use vegetable oil, vegetable lubricants, and vegetable-based diesel fuel. I remember in the early 90s when this was first becoming current in the construction equipment industry, that some of the manufacturers of equipment that used this boasted that the salesman could drink the oil. My experience in the construction industry is that the thing that gets salesmen in trouble more than anything is what they drink. But that's a whole different story. In any event, let's go ahead and start this up. There's a thermometer in here. I'm going to try. You're going to probably need to take the temperature of this fluid before you start. Otherwise, you'll have problems. And the temperature of this right at the moment is just about 20 degrees centigrade. We're not going to vary the temperature with this, but what we are going to do is we are going to vary our objective is to determine whether this fluid is Newtonian or non-Newtonian, and at the same time get an idea. The way this works, first thing you do is you select the spindle. The spindle actually that the machine is showing is correct. It's S61, it's an LV1 spindle. You'll notice if you look down into the beaker, you'll see a long cylindrical spindle, and this is a fairly common spindle for a wide variety of fluids. So what I want to do is I want to take the viscosity, and actually I have to enter the spindle because the machine doesn't know what spindle it has unless I tell it. And I want to take this at a variety of speeds. I'll start down and work my way up. And at different speeds, determine a different RPM to determine the actual, I wanted to determine the viscosity at various speeds. So I'm going to go way down here. And it starts off really slow. Whoops, that's the other extreme. Let's go ahead and hit the motor on. It's barely turning at 0.3 RPM. That means it takes, in round figures, 3 minutes to make one revolution. That's not much. And it's not recording much of a viscosity either. It's not recording any viscosity, in fact. So we'll kick it up. And now we get to the point where every 2 minutes it makes a revolution. And that's not doing us much better either. You need to wait a second when it gives you a reading for everything to stabilize. And you'll see that when we actually get into range. And then we have 0.6, and you can read the results straight off of the panel. There's no conversions like we used to do with the Thomas Stormers, and I talk about that in my variations in viscosity monograph. Now we're up to 1 revolution per minute, and we're not doing much better. But let's keep going. At 1.5 revolutions per minute, still nothing. 2. Usually what will happen is if it gets a reading, it will determine this, it will give you some kind of reading, but it takes a little bit to actually hone in on what the viscosity actually is, or what it measures it to be. 2.5. And we got a little bit of a brief, but it decided it was going to beat a hasty retreat from that. 3, it's still not really doing much. That's pretty slow. That means that it basically makes a revolution every 20 seconds, which is faster than we started with, but it's still. Wait a minute. Yeah. 4, it's starting to try to get something. It's very difficult to see it rotate at this point, but it is rotating. Now it's giving me a viscosity of 66 centipoises. However, it's also telling me that it's only using 4.3% of the machine's available torque. What that means is that to get a reasonable reading out of this machine, it is required that you get at least 10% available torque. In other words, that percentage needs to be at least 10 for a meaningful reading. So let's keep going up and see what happens. Obviously, the more RPM we put on it, the more torque, but it's not even giving us a reading at this point. It doesn't really like much what we're doing. But there he comes. But it's still at 4.7, 4.6. I would not include any reading below 10% of torque in the results. Not at all. Even if they look right. And we go up to 6. And again, it's taking a while to find out what the readings are. And it's giving me a range, but it's still below its maximum torque. It's trying to hone in on something, but it's just not enough torque to really make a reasonable reading. We've noticed through all the devices we've had in this course that the extremes, particularly the low end, we saw this with the pressure gauge tester, is not the best part of it. Now we've got a 10 RPM, we're actually starting to get some reasonable readings. We're actually above 10.1, we're barely above the threshold, and we're getting a reading. We just keep going. I'm just going to go step by step up here. Now we're in the range where it gives readings, and we're just going to keep going and see what happens. Now notice we've hit an error. The reason why is that we're exceeding the torque capabilities of the machine. The fluid that I'm using is a mixture, 50-50 mixture of hand lotion and water, or body lotion to be exact. And I'm already in trouble with it. Now I'm using the same spindle that I had before, but this is the first reading I've gotten. I started from the bottom as I did before, and this is pretty much the first reading I have on it, which is 2 RPM, and I'm already at 95% to torque. Obviously this spindle is too long for this, or it basically has too much surface area, is to be more precise, to actually accurately measure this. So what I'm going to do is, instead of using this spindle, I'm going to change it to this spindle with much less surface area and see if I can get a better result. The next fluid we're testing is a 50-50 mixture of body lotion and water. And this fluid is mixed up, and the first time we tried it, as you remember, the 61 spindle did not could not properly give a measurement. So we've installed the 62 spindle, and now we have a situation where we've had to do some experimenting. But as you can see on the video, you actually are getting a viscosity at 20 RPM. Now, I found with this that the best way of testing this fluid is to start at the top and work my way down. And so I've experimented a little bit, and it takes some patience. As you'll see, we'll go to 10 RPM, or 12 RPM to be exact, and it takes a little bit for this machine to figure out what's going on. But there it is. It's not instantaneous. Just because the machine is digital doesn't necessarily mean that it's going to give you snap results. You'll notice that the torque, if we're going down to 10 RPM, it's doing fairly nicely. I found with this particular fluid that it's better to start from a more rapid spindle rate and go down. And it's still taking up a fair amount of the torque to actually turn this stuff. Turn the spindle, even as short of a spindle as the 62 is in this particular fluid. The 61 is over to the left next to the thermometer. Okay, at 5. And then we keep going down. Eventually what's going to happen is it's going to quit giving me any kind of result. 28.95, we're getting better results. Whoops. I need to turn the motor back on. I hit the wrong button. Yeah, get to another. Turning the motor off in the middle of the operation is not a good thing to do. Try to avoid it. And again, like I said, it takes a little bit of time to actually hunt and hone in on the actual viscosity for a given speed. And the lower it goes, the longer it's going to take to do that. And we're coming down very nicely in speed. It's having a hard time at this slowest speed to actually get a reading out of it. We may have to stop at this point. No, we don't. There we go. I think we may be reaching the bottom of this process, so okay, let's go ahead and stop. No, there you go. We got another reading. See, it pays to be patient. Let's just go down a step. Some of you are probably already beginning to figure out what's going on here. I wanted to discuss the whole issue of shear rate and how we're going to deal with it here in just a minute. Once we get all three fluids tested. Okay, I'm going to go ahead and stop. I think we've pretty much accomplished what we've set out to do. And now we're going to proceed to the next fluid from here. Consider the case of the glycerin. The glycerin is fairly thick fluid, and so based upon our experience, my experience with the older viscometers, I decided to use the number 62 spindle. And I think that choice has been vindicated because, as you see, and actually the viscosity, it's kind of increased a little bit. At 50 RPM, we're at the top of the limit. So with that in mind, let's decrease the speed and see if we can get some reasonable results, and we'll work our way down. Yeah, we can. Go, you can see it a little easier to see. Actually, I'll just rerun the 50 RPM results, and they exceed the, they're right at the top. They're right at the very upper limit of the device's torque capabilities. Now we'll go to 20. And we go down to 12. So this spindle is pretty well suited for this particular fluid. And we go down to 10. Let's see how much. I don't think this is going to go any lower than that without getting out of the below the 10% range. And that's exactly what's happened. We're down below the 10% range, so I think it is time to stop. That concludes the actual data collection phase of the experiment. Now you have to reduce it. To reduce it properly, you need to understand what we're really looking for, and that actually is a lot of where I see a lot of students going astray on. And so I'm going to try to make this as simple and clear as possible. You have 3 sets of data with the independent variable being the RPM and the dependent variable being the viscosity. Now, if you remember from the lecture, and if you look into variations in viscosity, we have a graph which actually shows you what to expect out of Newtonian fluids, pseudoplastic fluids, and dilatant fluids in a situation if you actually will plot against viscosity against shear rate. Now you must ask, well then, what do I do? With this viscometer, it is possible to, it's possible, easily possible, to determine the shear rate of the fluid using the viscometer. And you can do a little research with Brookfield's materials, which I've put on my website, in order to give you an idea of what is happening when you can do that. I'm going to take a little bit of a shortcut, and I've done this in the past, and many students find it confusing, but I want more of a qualitative idea than a quantitative. If I consider shear rate, and I consider a cylinder, I've got 2 different cylinders. One is a long cylinder, and one is a short cylinder. And both of these cylinders have the same diameter, or the diameter is constant in both cases. And they don't have to be the same, but they're both the same, and it's a constant diameter. And I rotate that at a certain angular velocity. And we're going to see this again when we get to rotating drum. But in any event, the tangential velocity at the surface of the spindle is equal to the radial velocity speed of the motor turning times the radius. And as a result, we can directly relate the shear rate to the speed of the motor. What I'm proposing for you to do is to skip that step of converting. If you want to convert this step, and there's some other conversion factors you need to consider, but let's just skip that step for a minute, and let's just plot RPM as the independent variable on the x-axis and viscosity as the dependent variable on the y-axis. And basically what you're going to have is the same result. Obviously, for higher RPMs, you have higher shear rates. For lower RPMs, you have lower shear rates. And you can actually plot these and look at a qualitative way to see what's happening. If your viscosities decrease with increasing RPM, then you have a pseudoplastic fluid. Oh, excuse me, if they decrease, yes. If they decrease, you have a pseudoplastic fluid. If they increase, you have a dilatant fluid. And if you're in a situation where they're more or less constant, and that's where a lot of students get into trouble, then you have a Newtonian fluid. Your job is to take these and plot these and determine whether you have one of those 3. And with the now, one mistake I do see often is that students will allow their spreadsheets to do their thinking for them. They will basically say that they'll look at a Newtonian fluid, for example, and they'll see that the variations in the data determine the y-axis. And when they do that, they get a very narrow range of viscosities, and the variation looks very large. And they do a trend line plot, and they get a variation, and it looks, and they think, well, it must be pseudoplastic or it must be dilatant. When in fact, within limits, the range is Newtonian. And in fact, like I said, the Brookfield materials have some information on how to determine whether a fluid is Newtonian or not in terms of the way it varies. So you might want to look at that. But don't be fooled. Always, the easiest way to avoid problems is always plot your y-axis with 0 at the origin. If you do that, then if you force your spreadsheet to do that, which is very easy to do, then you'll discover the really significance of the variations in viscosity with rotational speed and ultimately with shear rate. So that's the biggest mistake I see. Take a look at what, it's just like I told you in the first lab experiment, the data least squares and curve fitting. Don't just take the results your spreadsheet gives you blindly. Look at them, think about them, study them. Don't just don't take anything on face value. Look at it and see how significant it is. In any event, that's it for this lab, and thank you very much for watching, and God bless.